Okay, so thank you for having me. Thank you that so many people connected to this talk. So I meant to present one paper. This paper was published in Journal of Physical Chemistry Letters in 2018. The lead author on this is Scott Jensen, my former graduate student. Now he is a postdoc at Sandia in New Mexico. So he decided to kind of quit synchrotron, unfortunately, and move on to, you know, to other things. But basically, the idea of this talk is to see what's happening with the, you know, atoms or molecules when we try to interrogate them at free electron laser. And I have like few very basic introductory slides, and I go deep into the details of this paper. And then I also have a few slides on photosystem too. So again, like we can see how we're doing with the time. I can probably take the questions after this first part and then see if there is interest to you know, review a few more slides. Okay, so I'll start with very general introduction. Is actually slides once I presented at crystallography community kind of, and I was trying to advertise that it's really nice to have spectroscopy and crystallography sometimes done together, and there can be benefits. So basically, in the very broad terms, when we talk about the spectroscopy, it's interaction of light with matter. Everyone probably knows who connected here. And we can have at least two major types of spectroscopy. We can look at the absorption, or we can look at the emission of the photon. And here you see the scheme when a photon is absorbed, resulted in photoelectron, and the emission then proceeded, and we have multiple wavelengths emitted in any particular case, but we can design here a good spectrometer to resolve with pretty high resolution any particular emission. And if we want to analyze our results, we have all the tools of quantum mechanics. So it's all atom is well understood. So we know the energy of those transitions. We know selection rules. We can try to compute everything what's been measured. So it's a very nice technique for many cases. So even if you're a crystallographer, which I don't think we have many on this call, but X-ray spectroscopy can help you a lot. We can fully characterize the electronic structure of any given specific element. And if we're talking about moving to free electron laser work, we can also do time-resolved spectroscopy. And we can follow this evolution of electronic structure in time, which is very interesting by taking, you know, spectroscopic measurements. And then there is this third point here, measure the extent of sample ionization in the XFEL pulse. So I don't think anyone has any illusion about the real situation which samples undergo, even if it's experiences 40 femtosecond X-ray pulse. And here we pretty much will show how spectroscopy can help to track those multiple ionized states. And again, like this was for crystallography, they can inform you on the crystal hits if you have any other problems, and only requires space at 90 degrees. So pretty much the hope is that many experiments at free electron laser, they can co-integrate the spectroscopy, because you can record spectroscopy at 90 degrees. So here are the main X-ray emission lines. They can be of interest. The most intense, so basically you ionize the atom, you remove this you know, electron, and then there are multiple transitions. So the major one is 2p to 1s, we call it K alpha. And as you see, there are two peaks. And again, sometimes when I'm talking to students, I'm asking them to explain why there are two peaks. So here I want to ask this question, but it's a spin orbit coupling of the 2p level is manifested, and there's two peaks. But what's with my voice? They have weak they have weak chemical information. Yeah, so we can record, we can see the splitting, but let's say if I want to compare a particular, transition metal gaining or losing one electron, it might be shifts, might not be very visible. Then we can move to 3p level, emission from 3p level, and this starts to become interesting. Why this starts to become interesting? Because again, if we are looking from biophysics perspective or catalyst perspective, there are a lot of 3D transition metals out there functioning in enzymes or in catalysts. And they usually function by redox reactions. But all this chemistry is happening actually at 3D level. But we don't have a really good measures, at least not with the hard X-rays of the 3D levels, but 3P level is interacting strongly with 3D. And basically this interaction is kind of reflected in this Kbeta lines. The downside, they're about 8 times weaker than K alpha line, but they're supposed to carry more information and they can carry the information about the spin state of those 3D electrons. For example, if all the 3D electrons are unpaired, it will be one signature. If some of those electrons are paired, it will be different signatures. So for example, iron, high spin, low spin, you can distinguish very well. So we did a lot of studies with the manganese. For manganese, the line will be shifting and so on and so forth. There is even weaker transition that if you go into the huge panes, you can record it. This one, which is 500 times weaker, it's from the valence level. So it's also, we had some papers on this, this can be interesting, but that's not the topic of this talk. So the topic of this talk, whatever you will see spectra, will be Kbeta emission. So dispersive. So whenever we do that, there are different technologies how to record. As you see, those spectra are pretty sharp. So if you want to record them with high energy resolution, you have to design a certain instrumentation. In the past, there were a lot of instrumentation using the Roland circle, and then you have to move your spectrometer and detector synchronously, and then you will record the spectrum point by point. That's how it's been done at the synchrotrons. It's very, very non-optimal for any time result experiments. So that's why people are developing dispersive spectrometers. For example, this one, top one, is photographed inside the LCLS vacuum chamber where combined crystallography and spectroscopy experiment was done. So it's very expensive spectrometer published in this reference. And as you see, you have a position like the picture B is the image on the position sensitive detector from the crystals in the spectrometer. They all multiple crystals focused in one line, so it takes time to focus them when you align. So it's alignment is pretty time consuming here, I have to say. Yeah, so what do you see on this screen? So you see basically this manganese Kbeta X-ray emission, and you can convert this image into the spectrum if you calibrate the detector, and you can record the data. And basically the data I'm gonna present today, which are from this 2018 Journal of Physical Chemistry Ledgers paper, they were all recorded with this spectrometer and doing this kind of things. But also in collaboration with Jerry Seidler, we developed things that we use at the synchrotron. So this is what we call here in this picture is the first generation manganese Kbeta X-ray emission spectrometers. Is like a small box here, and Pilatus position sensitive detector is on top. So the PS2 can be screened, even PS2 can be screened in this small sample space. And a happy graduate student who is now assistant professor at Emory. She started at Emory. Actually, I feel really sorry for all the new assistant professors who started this year because they just studying their labs and suddenly everything is shut down. Yeah, so she's in this situation, but we will continue to collaborate. I'll show you later something. So basically, yes, so different types of designs of X-ray emission spectrometers, and you can collect beautiful data and be happy. However, this bottom line, as you see, the bottom line is not focusing optics. For photo system 2, which is extremely dilute system, it's always a struggle. So we always want to have more signal, better signal to noise. So we spend another PhD another PhD student time on moving forward. And again, in collaboration with Jerry, we developed this focusing von Hammer's. And you see, this is the spectrometer box. It's a little bit bigger box, but still quite portable. And this is manganese Kbeta lines on the position sensitive detector, which is again Pilatus. And here is some procedure of preparing those band analyzers. And now we're trying to repeat it. So we're trying to build iron spectrometer and they will be different material, and we would just kind of shut down in the middle of the process. So we have where we got those rectangular wafers and we send them to polish, and we were supposed to start this step and then we shut down. Okay, so basically that's another type of spectrometer. So here there is some comparison of the performance and price. So dispersive X-ray emission spectrometers. So this is the first generation that Kate Davis used. So the crystals were gallium phosphide. The energy resolution was 0.3 V. Solid angle, here we wanted to improve. The cost was about $1,000. So here is the LCLS spectrometer, 0.55 EV, much bigger solid angle, and significant increase in the cost. So basically, very few single research groups. So it's more like a facility group. So this is the spectrometer developed by Scott. So here the energy resolution is so good that we were actually not able to precisely measure it, only estimate, because when we record those emission lines, it's a convolution of monochromator resolution and spectrometer resolution. So in this is a solid angle for single crystal, and with 3 crystals you can improve. So as you see, you are not as bad compare like 165 and 70. And also the cost of this one was very tangible. So we have a manganese K alpha design, which has not been built. And we have iron Kbeta spectrometer, as I said, under construction, which should be very similar to this one, but with lithium niobate crystals. So we have to see how they will go through all the procedures of dicing and bending and binding them and so on and so forth. But probably as soon as we open, maybe another 2 months till we can commission it. Okay, so now get into those LCLS data. So here we focus now on trying to see extent of sample ionization, and here, this is a table of content figure from this picture. So basically, this is a quick snapshot of what we are looking at. So we have a very simple manganese 2+ compound. It's just solution of manganese 2+ ion in ethanol, which we are jetting at LCLS. And we are spanning the 2 orders of magnitude in number of photons in our X-ray pulse, and you'll see more data. And you see that there is a quite dramatic change in the spectral shape and position when we go to the stronger pulses. Okay, so imagine we have this kind of data collected, let's say at multiple energies and at multiple intensities, and we can kind of gradually see how this change develops. What do we need to consider to understand it? So at the synchrotron, we're only dealing with a kind of single Absorption event, this is 1s electron level. We can absorb photon and move one electron into continuum. We have a hole, and we can repopulate this hole via K-beta emission, K-alpha emission, very well known to all of you. There is Auger decay as well, not as pronounced for heavy elements, but still should be taken into account. And no decay, there is a time evolution to all of that. However, when the sample experiences this extremely short and extremely bright XFEL pulse, there could be a second X-ray absorption. And then you have a significantly more involved situation because you end up with partially ionized states. Okay. So this is more data. So the data were collected over 2 beam times, and the data were collected with a different pulse duration because we wanted to understand not just intensity effect, but also the pulse duration effect, because often people, go into shorter and shorter pulses, people hope to outrun certain processes, like they can definitely outrun the chemical damage, which is more common at the synchrotron. Here, that's why measurements were done with, measurements were done with 20 femtoseconds and 40 femtoseconds in one run, and the energy, the total photons per pulse were scanned from 10 to the 10 to 10 to the 12, this situation. Another beam time, it was 16 femtoseconds and 36 femtoseconds, and again from 10 to the 10 to 10 to the 12, slightly different absorption energy. The top one was 6.9 keV, the bottom 8.7 keV. This is just, connected with the other experiment, which was happening in parallel, like some crystallography studies. Okay, so also another thing, one beam time did not have a K-beta prime. So pulse duration I discussed. Okay, so I wanted to also comment here. So during the second beam time, we were already able to sort pulses. So there was a pulse diagnostic in place, and we could sort pulses, individual pulses, by their pulse durations, because this is also something which is changing, because you can say 16 femtosecond, but you might get a pulse which is only 7 femtosecond, or you might get a pulse which is 20 femtosecond. So in one of those beam time, we had the capacity of sorting by pulse duration, which was exciting. So maybe you can ask me, you say, okay, so you're mostly talking like, you're impinging this 6.9 and 8.7 keV photons on dilute manganese 2+ solution. How do you actually know that the 1s, which plays the major role? So we are happy that in atomic physics, everything is very well understood. So the cross sections for different processes are well understood. So I have this table to convince you that indeed the majority of the process is 1s electron absorption at those energies. Yeah, so there are some other minor processes like 2s absorption, but it's below 10%. Okay. So Scott spent about 1 year trying to model in this data. So it was not easy because there are many states, there are many processes. We know their lifetimes, we know their probabilities from, atomic physics tables and books. And he had to build this equation model. I'll try to explain it a little bit. So it's a rate equation model. It's like in the chemical kinetics. So you have multiple species and they can interconvert, and you try to track the evolution in time. So rate equation model, and what is the input? The cross sections. obviously, and excited state lifetimes, and those were calculated by XAtom program. So the photon flux density and the pulse duration, a system of equation then created by considering the absorption of X-rays that ionize 1s electrons and the decay pathways that fill the 1s hole. And we discussed those decay pathways here. So they will be K alpha fluorescence, K beta fluorescence, and they will be Auger decays of several types, and they were all included. Okay, a symbolic rate equation shown here, and there is some kind of attempt to rationalize it on a schematic way with different colors. So basically there is ionization and decay, and then the second ionization, second decay. And as you see, we went 1, 2, 3 steps at least, what is colored. And this can happen all within, you know, that 20 femtosecond or 40 femtosecond pulses. So using those rate equations, we can predict, and here are the pure computational prediction, which again Scott generated. So what do we see here? So there is a blue color and red color, and there is something which we call a linear regime. So basically, what is this plot B? Let's say we record the total K beta fluorescence in those multiple decays. And the blue one is like classical fluorescence that you will see at the synchrotron. Yeah. So contribution to the total K beta fluorescence based on decay from 5 different states. And this is singly ionized state, and others are multiply ionized. And alpha is a very important parameter. I have to clearly define it. So the alpha simplifies everything. So alpha is such thing. So where is my mouse? Okay. So it's an absorption cross section of 1s level. 0.5 is a coefficient, and then it's a photon per pulse per area. So basically it renormalizes per area, so you don't need to worry about the beam size, and it renormalizes for energy, so you don't need to worry that one experiment was at 6.9, another experiment was at 8.7, because that will be in this absorption cross section. So basically, it's a kind of shows how many photons each individual atom will see in some sense. Okay, so here is the alpha. So basically, the bigger alpha means the more intense X-ray beam. And we see that the classical fluorescence is given smaller contribution, and emission from ionized states give a contribution. Now, if you ask, can I perturb this by using a different pulse duration? And this is the pulse duration on femtosecond time scale. Like, you know, we kind of zoom in into the very early event, and we see that, so depending on the alpha, basically, alpha is the one which controls it, but the time does not change. Pulse duration doesn't change anything here. So we can come back to this later in the discussion. Okay, so what has happened in this analysis? So we have those experimental data, and we look at different options, how we can analyze them. And it's very common to look at the first moment of the K beta 1,3 peak. And what is plotted on this analysis scheme is a change in the first moment. So basically that tells us about just the line position. And we know for manganese that this reflects the oxidation state. So the 0 will be manganese 2+. So if we would be in a perfect world, you know, sitting at the synchrotron, measuring slowly, and we're measuring manganese 2+, we should obtain all our first moments close to the zero. However, we are at a free electron laser and we're blasting it with, you know, 10 to the 12 photons in very short pulse. So we are starting seeing some other things as we increase the number of photons in the pulse. And how bad are those other things? So you see, this is the next level, and this is already formally manganese 3+, and this is manganese 4+. So we can perturb the spectral position, at least spectral position analyzed by the first moment, to a significant extent, to such a significant extent that it does not even look any longer as manganese 2+. It becomes, you know, it becomes broadened and shifted, and it's all shifted to oxidative state. That's a note. And all the dots here are experimental data, as you see, different pulse durations, different energies, all plotted versus this super convenient parameter alpha. And the dashed lines are those kinetic models that Scott spent 1 year to build those equations. So you see, we were actually shocked how well those experimental data overlay with the kinetic models. And we have one set which deviates, and this is the one which had the longest pulses, 40 femtosecond pulses. And I'll comment on it later. But then, you know, manganese is very interesting because we try to understand how photosystem 2 works, which is the protein which gives all the oxygen we breathe, all the oxygen in our atmosphere, and it has 4 manganese ions in the manganese 4 calcium cluster. And people fight really hard, struggle really hard to understand how this system works, because you can also use it for alternative energy. And of course, that system has very high priority at free electron laser. Many people went and tried to measure crystallography of that system, and this is what they got. So if you scrutinize, there's crystallography papers done on photosystem 2, time resolved X-ray diffraction, you are getting into the ballpark of those processes. And again, like, we have a very clear analysis of what it does for your X-ray emission spectra. We don't know what it does for your crystallography data, but definitely multi-photon ionizations will be present because it's in this range of alphas. And what else I wanted to say? Here I had a comment. Okay. Range of crystallography. Okay. Okay, so yeah, I had a comment which skipped my brain, but might come back. Basically, now I'll have a summary of that study, and I'll take questions after that. So the summary is what you have seen. Okay, so I know what I wanted to say here. I wanted to say here at this point, I know that other people were doing damage studies. I don't think people published much of, you know, similar type of analysis where they kind of try to put some limits on, basically where they try to use spectroscopy to understand what is actually happening with the atoms as we probe them with free electron laser. Because this orange, like, okay, so this pink area, what we call the linear response. So we think that this is the good place to record your data, at least for the spectroscopy. But as I said, the real experiments are happening in this range because we understand we want to have more, more signal, more intensity for the diffraction. And I know there are more data out there. I don't think there are, I mean, we kind of, it will be beneficial to kind of put together those measurements and understand more about things happening in terms of like this different type of damage. Okay, so summary. So rate equation model quantifies the percentages of recorded X-ray emission from atoms that have undergone a single or multiple sequential ionization events. So basically the rate equation model, in our opinion, was successful. Excellent agreement between the theoretical model and experimental observation has been demonstrated. Using the rate equation model, we provide a simple method to estimate the percent of classical fluorescence versus fluorescence originated from sequentially ionized states and the associated, at least first moment shifts. Deviation from sequential ionization model is attributed to electron cascade. So what we are thinking, this blue line deviates from the calculation is because our calculations, they don't really look at those for the electrons which escaped. But on the time duration of 40 femtoseconds, it looks like at least we attribute this deviation, so kind of bigger effect on the spectra than purely coming from sequential ionization. We attribute it to those photoelectrons, a kind of having enough time to interact and do some damage or some additional chemistry or physics to the manganese ions. Other thing I wanted to comment here, except like, trying to, gather more data and continue this analysis. So what we were trying to do, like when we got those data and published this paper, we tried to say, okay, can we really compute? So I have a note here to myself, theoretical modeling still lags behind, yeah? So even for this simple manganese 2+ in solution, I still have great difficulties to compute X-ray emission spectrum, Kbeta X-ray emission. But now I say, okay, I know what is the second most common species. Let's say this is this doubly ionized state. Forget about it. Like I could not entice any theoretician to compute how the spectrum of this state would look like. And, we tried with one person who worked with me, so I have several papers with him, and it just got nowhere. So I think also would be interesting because this is just empirical analysis, yeah. So the spectrum is shifting, but we don't know, how the spectrum should look like from this species. Okay, I think this is there are some recommendations here. They may be very plain vanilla, but okay, since sequential ionization is dependent on alpha, lowering the number of photons, increasing the beam spot size, and increasing the incident photon energy all reduce the effect of sequential ionization. Out of the methods for reducing first moment shifts, only increasing the X-ray spot size will not have a proportional reduction in the signal. So basically defocusing, and this is what crystallography people don't like to do, I would imagine. Judging by our data, higher incident photon energies have advantage over beam attenuation in that they will also reduce effect from photoelectrons of low Z elements by lowering their cross-section. Shorter pulses will also lead to fewer electron interactions within the sample during the duration of the pulse. So it looks like, using the shorter pulses here, you can outrun the effect of electrons, but you cannot outrun the effects of those sequential ionizations unless you go to like attosecond pulses. Okay, so I think this is a good summary slide. I'll like to take questions at this point.
Thank you. That's a wonderful presentation. Why don't we start with Matthew, Matthew Marcus, that is. Could you unmute and ask your question?
Yeah, in that slide that was headed first moment analysis, it looked like the broadening was greater for the longer pulses for a given photon dose, and that seemed kind of counterintuitive. I would have thought that the effects would be greater for shorter pulses, because with longer, after all, imagine a pulse of 1 second, then you would have no multiphoton ionization. So,
but this is for total like you see your shorter pulse and your longer pulse has the same number of photons per pulse.
Right, but imagine the same 10 to the 12 photons in 1 second. You'd have no multiphoton at all.
Yep.
And so now it does look like normalizing by alpha gets rid of most of that effect. Only the blue line shows anything significant, and the explanation about damage may be the right way to go. But then I also wondered, how did you get all the parameters needed for the rate equation? There's a gazillion parameters in there.
Yes, it was a struggle, and mostly like X atom they provide. So basically all what went to this modeling is a X atom. And as I said, we have our most common species at certain times, but we could not proceed to more modeling, modeling, let's say, what are those spectra which we are adding to the normal undamaged spectrum, yeah?
Right, and it also seems to me that that this alpha parameter would be the controlling one only for pulses shorter than some certain time. As I say, for a 1 second pulse, no matter what alpha was, you would have no multiphoton. So there must be some time above which if the core hole relaxes before the next photon hits.
I understand. Yeah, so you pretty much that it says photon per pulse, but
there's no time involved.
No time involved in this parameter. Yeah. Yeah, it's a good comment.
Okay, we've got 2 questions related to matrix effects. I wanted to start with Matt Newell, and then after Matt, go to Jacinto Sa. Matt, are you there?
Hi, sorry. Yeah, I was wondering if your alpha parameter was including the absorption cross-section or the total attenuation, and then also does it include the matrix, or is it just for the manganese?
Yeah, so our matrix is like low Z, so it's a manganese 2+ in ethanol. Maybe there is a little bit of water. So we kind of say, okay, so this is low Z, this is like a protein environment. We have not included any of it in the model. That's for sure.
So what's the manganese concentration then?
So I think it was within 1 millimolar. I have to check. It was pretty dilute, and the paper definitely has it.
So then what fraction of the 6 to 8 keV X-rays are being absorbed by manganese versus the solvent?
That's a good question.
Because what's the source of the beam damage? Is the beam damage because manganese is being multiply excited, or because the ligands are breaking, or because the water is absorbing the X-rays and creating photoelectrons?
Exactly, yes. So we think because we had another damage studies for photosystem 2 where we attributed, it was at the synchrotron, and we attributed all the damage to, photoelectrolysis, oh my God, photolysis of water. Yeah, so when you do things at the synchrotron, everything what happens to manganese is coming from the environment. Right. But what we thought here, that there is no time for chemistry. Let's say you created OH radical, or you created solvated electron. So those are the main things which work in the synchrotron damage. we think that within, let's say, 20 femtosecond, we don't have any chemistry happening with, let's say, solvated electron or OH radical at this point.
Mhm.
We have solution scattering data which have not been analyzed yet. So we are very curious about, changing the environment of this manganese. And we might have a data, I have a new student kind of slowly learning those things. But we cannot say anything. But again, like, I welcome input, because this is not our main direction. We do many other things. We do a lot of spectroscopy and artificial photosynthesis and brain imaging. So I'm welcoming the input, on other people looking at the similar things, more involved models which would have, environment and so on. So why, like, basically, to answer your question, we excluded environment because we thought there is no time for chemistry to happen on those time scales. And basically, as I said, like, if our rate models would be, significantly off, we would look for additional, additional explanation, or we would include additional things into the model.
Okay. Jacinto, are you there for a question?
Yeah.
Yes.
I mean, I think my question follows what Matt say. I mean, I think this is quite particular for photosystem too. I do not agree that the ionization, high energy ionization electrons will cause havoc within less than 10 femtoseconds. It just doesn't happen in PS2 because the manganese center is quite buried in the protein. But that doesn't basically turn it into a general case. So I think Matthew is right. The matrix here is quite important, and it's just fortunate that somehow in the manganese, in the photosystem too, you have basically a very well protected manganese center that is shielding, because we shown in the iron complexes within a few femtoseconds we have iron wind oxidations 5 and 6 just with ionization electrons coming from the solvent.
Can you send me the reference to this paper?
Yeah, I put it on the chat already.
Oh, excellent. Yeah. So again, so photoelectrons, as I said, we think that the blue curve adds the effect of photoelectrons. Those are all for manganese 2+ in solution. There is no PS2 data here. It's just the red box is the range of PS2 reported. So this is the alpha parameters in which the crystallography things are reported. And again, if I have a few more minutes, I can show the status of the current crystallography and what we know there. Okay, but I'll definitely study more literature.
Okay. We don't have any more questions. If you want to show just 2 more slides, perhaps on the XRD, that would be fine, and then we will, we'll end.
Yep. Okay. Excellent. So I want to kind of briefly summarize the evolution of PS2 XRD data. So basically, interesting, has such a line here. Basically, we have tried to do time result X-ray emission spectroscopy at the synchrotron, and it was a big project which took many years. And the conclusion of this project was in 2015 when we posted things on arXiv, and then we had quite a long lag in really publishing it for various reasons. But basically, there's extensive time result X-ray emission studies looking at the most critical transition where oxygen-oxygen bond is formed, allowed us to propose this model. So this is the model coming from spectroscopy only. And we say there has to be manganese 4, short double bond oxygen interaction, and there is this characteristic distance 2.5 angstrom. And as I said, we had difficulty to publish in 2015. No one believed our model. So till in 2017 came the time result study of that state, which was actually indistinguishable within the resolution of crystallography from our model from 2015. The only difference was that this oxygen-oxygen bond was not 2.5, but 1.5. So, and people started talking, maybe there is a peroxide there or something else. Then another structure came in 2018, which said this distance is 2.09 between those two oxygens. And then another study came in 2019 that basically said, okay, now this distance is 1.9 angstrom. But my problem with all those studies that there is no model of photosystem 2 which would have 2.0 distance here. It's either 2.5 or it's 1.45. So it's either oxygen-oxygen bond is present or is not present. So basically, you cannot get the DFT calculation of any sort to give you that kind of distance between the oxygens, like in the real world situation. So I think now this is a kind of still open question, and people are trying to address it. We addressed it our way, so we again showed our model overlaid with that model. As you see, there's very high similarities, and we concluded that you can indeed move those oxygens together between, like this S3 state will have 2.5 angstrom distance. This S3 state with the peroxide will have 1.45 distance. And depending on the type of calculations you can do, the energy gap between those two can be as small as 0.2 eV. So, and this resulted in this proposal. So we propose that high energy peroxide isoform in S3 state exists, can be, you know, accessible there energetically, and then it can be preferentially oxidized by tyrosine Z in the course of final electron transfer, leading to O2 evolution. And this, so far, to the best of my knowledge, this is the only mechanism that explains the kinetic challenge, which is heavily discussed in photosystem 2 community since like 70s. Okay, I think this is a good concluding slide for the PS2.